Hello, welcome to another edition of James and Chris Science videos, where today we're going to be looking at moments and rotational forces and looking at what they are, the equation for them and a definition. I'm also going to go through some worked examples and show you a couple of practicals in the lab that we can do to prove that moments follow the laws that we're going to talk about. So here we go. Well, first of all, we're going to talk about what a moment is. And to understand a moment, we need to first of all understand what a pivot or a fulcrum is. Because when we talk about moments, we're going to be talking about rotation around a pivot or a fulcrum. So I've given you here three little examples. A fulcrum is a point by which objects rotate. So on a wheel, it's the axis in the middle, and it rotates around there. But if you've got a seesaw, it's the point where it rotates on there. And I've done a pair of scissors here, and the pivot or fulcrum on that is the screw that's in the middle, and that's where it rotates around. So to understand the fulcrum allows us to understand then the definition, which is a moment is a rotational force around that pivot or fulcrum. There is an equation for it. The equation is that moment equals force times distance from pivot. And I'm going to talk you through an example of what that means and how to work that out. So here's my example. Here is a seesaw and here is me, a little bit younger with no hair. I am sat on the seesaw and there's going to be two factors that are going to affect my moment. The two factors are the force and the pivot, for distance from the pivot. Now my force would be my weight. We discussed in previous videos, weight is measured in newtons. And I'm quite happy to tell you my weight is 1,100 newtons. It's 110 kilograms in mass, 1,100 newtons in weight. I've put myself sat on the seesaw at a distance of 2 meters. So the moment for me on the seesaw is 1,100 times 2. So I've therefore got a moment of 2,200 Newton meters. Now that's the unit at the end, Newton meters. Notice how they're together, and like algebra, if you put two letters together, that means that you times them. So the unit is an expression of my equation. Distance, newtons, times force, meters. Put the two together, you get NM, Newton meters. So what can I do with that? Well, I can now start looking at examples of what happens if I put something on the other side. So I'm going to put on the other side my daughter Emily. Now this is quite an old photo. She's actually 13 now. So I think she's 6 in this photo, and she'll be delighted that I've used this. But there we go. There she is. She, at the time, I'm going to estimate her mass at the time was 35 kilograms. So that would give her a weight of 350 newtons. I've also put her 2 meters away. And so that would give her a moment of 700 Newton meters. Well, so what? Well, what does that mean? Well, if I put them together, that means that I'm going to go down and she's going to go up because the moment on my side is bigger than the moment on her side. I've put this here in a little statement, and that little sign that looks like it's like a train station sign, isn't it? That means is not equal to. So 700 Newton meters is not equal to 2,200 Newton meters. Therefore, I will drop down to the bottom. Emily will rise. Now, if I want to balance, we need to get Emily's moment to equal my moments. And we've just talked about changing the distance from the pivot. So in my worked example here, I know on Emily's side, Emily was 350 newtons times by the 2 meters distance. So her moment was 700 Newton meters. Now I know my force was 1,100, and I want to work out the new distance that I need to go. So if I put this into my equation, I know that 350 times 2 is 700. So 700 equals my 1,100 times a mystery distance. Now, if I've got times 1,100 on one side, to move it across, I need to divide it by 1,100. So on the other side, I've now got 7,000 divided by 1,100. And if I put that into my calculator, that gives me a value of 0.62 meters. So if I shuffle along the seesaw and I sit at 0.62 meters away, then we balance, and look how excited Emily has become. Isn't that nice? Now what I'm going to do, I'm going to go to the lab now, and I'm going to show you some examples of moments in action. So I'll show you pretty much how this works using masses and a seesaw in the lab. And we'll come back and I'll go through a past paper after this and we'll summarise and finish there. So I'll see you in a couple of minutes. Okay, here we've got a setup where I can show you moments and look at the calculations we've got in a practical format, which is going to hopefully help you to see it a little bit more clearly on how to approach a moment question. So just remind you that the equation for a moment is distance from pivot times force. So the first thing we've got to do with any kind of example is work out where the pivot is. And the pivot is the point where the device will turn. And in this case, we've got a fulcrum here, and this will be the pivot. So on the back there's just a little line for it to sit on. Now these are not very good. You can see straight away they're not balanced and they're warped. So what I'm going to do is I'm just going to put a weight on them to calibrate the device. This we're just going to ignore this after this moment here. So I'm going to put it onto here, and where I put it on, I just want it so that it's balanced, so that it stays flat, slightly that way. Okay, so there you can see that's floating at the top. That's not moving either way down. That's calibrated. That is ready to use. So this is how it works. A moment is a force acting on a distance. And I've put numbers 1, 2, 3, 4, 5, 6, 7, 8, just to make it easy. 1, 2, 3, 4, and they can be meters, centimeters, doesn't matter. I've just put them on because this is just going to demonstrate the idea. I'm going to put 1 Newton at 3. So we can say the moment on this side, I've got a seesaw, and I'm just going to turn it upside down. So I've got 1 Newton, and that distance is 3. Again, I'm not worried about the units at the moment. This is just for demonstration purposes. So that would generate a moment on that side of 3. Distance is 3 times a force of 1. So the moment on that side is, I can't write upside down, 3 Newton. I'm just going to call it meters. I'm going to say that's meters. I know it's not, but we've got to put a unit in there. 3 Newton meters. So in order to balance, I would need to put 1 on this side, and the moment on that side has to be the same. So I've got 3 newtons per there, and I've got 1 here. I can put 1, and I put my 1 at 3, and it balances. Now, it has to be anywhere within the little squares for it to work. These are just not that accurate. But you can see, there we go, they're both in the 3, it's balanced. So 1 Newton in the 3, 1 Newton in the 3, balances. Now, if I take 2 masses onto this side, and I want to get that to balance, I now need to reverse my equation in order to get that to work. So 1 Newton times 3 gives me a moment of 3 Newton meters. To balance, I want 3 Newton meters here, but I've got 2 as my force. So in this case, I'm going to rearrange my equation. I now want the distance. So distance is going to equal, because moments is distance times force. If I want to move the force to the other side of the equation, I need to divide both sides by forces. So my distance, and I'm going to write this down here, D is going to equal my moment divided by my force. So my moment in this case was 3, because it's got 3 back to 1 front 3. Writing upside down is very difficult.
Doing a good job.
Yeah, I'm doing all right. So we've got to say that that moment has to be the same on both sides. So my moment is 3, and my force is 2, because that says that there. And so if I did that, 3 divided by 2 equals 1.5. So in order to balance here, I should be able to put 2 masses here at 1.5. Move it around slightly, because they can be anywhere within there. And there we go, it's balanced. So it does work. It does work. So I could give more complicated examples. I could say I've got here 2 at 8. So my moment for that would be 2 times 8, which is 16. So if I then said, so my moment is 16 on that side, I want it to balance, my moment on this side has to be 16. But I want to put my weights on the 4. So how many weights would I have to put on in order to make it equal 16? So I've got 16 here, I've got 4 there. So again, we can rearrange my equation, and this time it would be my force would equal my moments divided by distance. 16 divided by 4, which equals 4. So if I put 4 masses on here, you can see, again, I'm going to move them around slightly because it's just not that accurate, this piece of equipment. Slightly going there, so I'll move that slightly that way. And you can see that's getting there. Not too much. There we go. Balanced. Slight on this side, ever so slightly. There we go. Balanced. So, in order to approach a moment's question, you've got to take one side and consider this side like an equation. So one side as an equation, and you use the moment equals distance times force. You then take that moment that you got there, and you've got to put it onto the other side, rearrange your equation, to work out what it wants you to find out. Could be the distance, could be the force. And that's how to approach a question. If you approach it in that logical way, they're actually quite easy. One side first, use the equation, take the moment over, use it on the other side. Brilliant. So we've learned that to answer moment questions, we need to treat both sides of the pivot the same. Now, what I've put on the screen now is a past paper. This is a long time past. This is almost 15 years old, this paper. But the principle's still the same. So here is a question. James uncovers a large rock in the garden. He cannot easily move it, so he uses a fence post and lever to help him. He uses a round stone as a pivot. So here we've got a moment question. The horizontal distance from James to the stone is 2 meters. He pushes down with a force of 40 newtons and the rock starts to lift. So find the moment James is producing. You're going to need to use the equation that we've talked about, moment equals force times distance, to give us the moment. There's 3 marks. There is 1 for getting the equation right, 1 for putting the numbers in and getting the answer, and 1 mark for putting the correct unit on your answer. It's an easy mark to lose, that 3rd mark. You need to make sure you've got the unit. It then goes on to say the horizontal distance from the rock to the stone pivot is 0.5. Ignoring the weight of the post, calculate the weight of the rock. So we know the moment on one side and we need it to equal on the other side. So just like I did in my example with me and Emily, I now need to rearrange my equation and see if you can work out what the force of the stone pulling down was. In reality, the post does not have weight. Does have weight. State whether this means the answer to the rock is less or more. That I'm going to let you decide. Do you think it'll affect it? Do you think it will not? And state 2 things that James could do to increase the moment which he's producing. What could he do on his end in order to increase the moment? So there's a couple of things he can do there. Let's summarize. A moment, then, is a rotational force around a pivot. There are lots of devices that use this, from doors, levers, lots of different examples that you'll see around your house. Anything that involves any kind of rotation will be a moment. The equation for moments is moment equals force times distance from pivot. Learn that equation. You will need to know it off by heart. The unit for moments is Newton meters. It's such an easy mark. If you know your units, there is 1 mark guaranteed every time for knowing the units. To achieve balance, the moment needs to be the same on both sides of a pivot, and we can use that knowledge to understand how to transfer numbers across other side of the pivots. And last of all, Emily used to love seesaws. I don't know if she still does, actually. We haven't been to a park with the seesaw for a long time. But it used to be a family favourite, and I quite miss making a bounce 1,000 miles up in the air on a seesaw. So there we go. There's my summary. Thank you very much for watching. Hope to talk to you soon. Bye-bye.